Okay, good afternoon, everybody, or good morning if you're on the other side of the ocean. So this is the latest machine learning for science seminar, and it is my great pleasure to introduce you to the speaker for today, who is Heather Kulik from MIT. So for those of you who don't know Heather, she's an MIT graduate, I believe, at the time in the group of Nicola Marzadi. And then she took a couple of postdocs on the other side of the United States, in Lawrence Livermore and Stanford. And then she came back to MIT for a professorship position in the Department of Chemical Engineering. And I think lately she has been developing quite an interesting program in looking at how machine learning can be combined with essentially theoretical chemistry for problems such as catalysis and so on. So I guess without any further ado, I just would like to give a stage to Heather. Thank you for being with us, please.
Thanks. Thanks, Stefano. And I'm going to go ahead and try to share my screen. Okay. Just moving Stefano's face out of the way. Hi everyone. This is it's my pleasure. It's my first virtual seminar that I'm giving in these new times we're living in, and so we'll give it a go. But I'm sure there will be a couple of hiccups today. It's my pleasure to tell you about some of the work my group has been doing for the past 5 or 6 years on merging machine learning and high throughput simulation tools. And over what I like to think is a short time since I first started as a PhD student in Nicola Marzari's group, as Stefano mentioned, back in 2005, so about 15 years now, there's been a tremendous advance in the power of computing. And this has really allowed computational chemistry to become essential in strengthening understanding. Now, if you had asked me what I thought I would be talking about 5 years on in my independent career, it would be things like the protein hemoglobin, which is part of why we breathe triplet oxygen. So hemoglobin has this kind of cartoon structure, and inside hemoglobin is something called a heme, which is closer to what I'll be talking about today. It's the porphyrin. It's under the hood, and it also has a metal spin. And so if you give either of these structures, experimental structures, to a computational chemist, they'll do a really good job, as many of you know, of understanding how these systems work. Why do we bind oxygen? How do we release that oxygen in tissue and absorb it in the lungs and so on? But what we started to ask as a question instead was, what do we do to go beyond understanding, but instead to accelerate discovery, and particularly in this challenging world of open shell transition metal chemistry? For those of you less familiar with transition metal chemistry, I will go through some of the basics of that as well. But an important thing to understand is it took nature millions of years to come up with this heme and porphyrin structure. And so one of the things we might want to ask ourselves when we think about accelerating discovery is, which atoms matter the most? If I care most about this molecule's redox potential, or its structure, or maybe its ability to catalyze a reaction, maybe different atoms matter more. And we need a language for that in order to be able to start to build our own porphyrins, our own new molecules from the ground up. And why do we care about this at all from a practical perspective, from an engineering perspective? Well, it turns out if we think about some of the most selective catalysts, many of them have a lot of things in common with this porphyrin. So if you go from single atom catalyst to emerging MOF catalyst to molecular catalyst, all of the most selective catalysts have this single site with organic bits around. Similarly, we can think about applications I'll talk about today in energy storage or even in gas separations. Often when we think about opportunities for molecular and materials design, some of the best materials we can come up with have this metal center and organic bits around. In the physics community, there are many other applications as well. So this idea of having a language for for molecules that helps us accelerate their design is not new. And there are lots of ways we could think about this. So in the solid state community, there was a lot of high throughput screening and discovery efforts pioneered by Garrett Sater, Stefano Curtarolo, Chris Wolverton, and many others. And then even going back further, the organic chemistry community in the 80s and 90s through therapeutic drug discovery had developed a lot of really handy tools. So if you know the SMILE string of an organic molecule, you can very easily generate structure, you know its connectivity. Many low-level, high-throughput methods such as force fields and semi-empirical theories work well here, and there are multi-million molecule-size compact databases of all of these SMILE strings that even if it's not the whole chemical universe, it's a very big chunk that we could think about for discovery. And then concepts of molecular similarity are well defined here. So we can say, I don't want to study all couple million molecules, but I can focus on the 10,000 most distinct. So if we try to use and extend all of these tools, that's the first thing my group did. For inorganic chemistry, we run into roadblocks. So the idea of using a SMILE string is going to be limited to a single oxidation and spin state. And even if it did work, we would want to understand the effect of this on structure, which we can't easily through SMILEs. Most force fields and semi-empirical theories, especially 5 years ago, didn't even exist for open shell transition metal chemistry, meaning DFT is the absolute minimum we can do, which limits how many new molecules we can study. And then the types of databases, while my group has worked with them, that are most accessible for inorganic chemistry are these experimental structures of synthesized, crystallized molecular inorganic complexes. And so what we can see when we look into those databases is that experimentalists have studied porphyrins a lot, but it's not necessarily the fastest route to discovering what the next porphyrin should be. And then concepts of molecular similarity that would work for organic molecules routinely fail for transition metal chemistry. So what we did was take a divide and conquer approach, which I motivate by this fairly pedagogical figure here. If you look at the progression of organic bonds from a triple bond to a double bond to a aromatic bond to a single bond, they follow this very strict line. And that means that relatively simple models can predict for us how long the bond length should be of an organic molecule. But if you look instead at an iron hexacarbonyl complex and you keep the chemical composition the same, but you change its spin and oxidation state, you can actually span the same bond length variation on the iron-carbon bond as you do on the full range of triple to single bond on a carbon-carbon bond. And in fact, this relationship is highly nonlinear, which explains why there haven't been nearly as many force field and semi-empirical theories that work well in open shell transition metal chemistry, but it also explains and motivates why a machine learning approach that can learn these nonlinear relationships should be the way to go. But before we got there, what my group did was develop a code that underlies everything that I'll tell you about today called MLsimplify. And what we did in particular was say, okay, most of a transition metal complex is organic in nature. There we'll trust the force field, we'll exploit SMILEs, everything that works in organic chemistry. And then when we first did this, we put together a database of DFT trained values for the inorganic parts, things like the iron-carbon bond length, and then carried out a series of automation routines that allowed us to assemble transition metal complexes at the command line. And so this enabled the first automated command line structure generation and high throughput screening in open shell transition metal chemistry, where other fields such as solid state chemistry or organic chemistry was much more mature. And so this allowed us to do things like use SMILE string searches and dissimilarity searches for just the organic parts of these transition metal complexes and so on. And so this is about all I'll say about MLsimplify today. There's a Docker installation, Conda and GitHub, and so on. But just know that it's the glue and it's the engine behind everything I'll tell you about. And so when we first developed this code, the very first thing we did was we just went out and did high throughput materials discovery. And so we applied this in the context of functional materials, understanding things like quantum dot growth or catalyst design. And in the interest of time and the focus on machine learning here, I won't tell you about any of this work today, except to say that it allowed us in all cases to explore just enough space on the scale of a couple hundred catalysts to 500 catalysts or materials to break our chemical intuition to break expectations from prior experiment and discover ways to overcome rules in chemistry that people normally thought of. To put this in context, if I wrote a paper in my PhD, I would have expected to study 40 molecules, maybe at most, and come to a conclusion based on those 40 molecules. Simply by going to 500 molecules, we were able to see that there are ways and exceptions to break a lot of the rules that you can often conclude on the scale of 40 molecules. So we, by automating the approach, we increase things by an order of magnitude. By the time I get to the end of my talk, I hope to show you applications in the context of thousands and millions of molecules. But this is where we started, in the scale of these small chemical space neighborhoods of hundreds of molecules. And what we realized is that we were not going to get to this picture of seeing what the next porphyrin was. We were not going to discover what the next porphyrin was in this way. We could do lots of cool science, but we weren't going to accomplish that. And that's because transition male complexes in particular inhabit a really large space. So I've already alluded to some of the knobs you can think about tuning when designing a transition male complex. One of them is spin. So just like oxygen is in a triplet ground state, transition male complexes in the mid-row can alternate between high spin that I'm showing at the bottom or low spin electron configurations. This is something like a D5 iron 3. And then each metal in the first row in particular, which will be the focus of my talk today, can sample a wide range of oxidation states. For instance, just iron complexes can sample iron 1, iron 2, all the way through iron 5. And these different electron configurations can have different spins and so on. And then simply the range of ligand type and size and chemistry is much more varied here than it is in simple closed shell singlet organic chemistry. So the simplest non-trivial transition male complex that's octahedral in nature is going to have at least 13 heavy atoms. In comparison to the organic chemistry data sets widely used in machine learning, this is much larger than the largest molecule typically studied. So what we can conclude is that we have a bunch of big molecules, there's a lot of knobs to tune, and we need to study a bigger space than even the most high throughput accelerated DFT is ever going to get us to. And so we needed something faster than DFT. And the way we got into machine learning in my group is in about spring 2016, a first year graduate student in my group, John Paul Janae, came to me and he said, I'm taking machine learning class. I knew he was taking a machine learning class, but he said, we have homework for a final project. What would you like me to be able to predict? And, honestly, I was feeling pretty good about myself as a scientist, as an engineer. And I thought, let's make this hard. I mean, when most of us who are established in the field first came to machine learning, not all of us came to it thinking that we really thought a machine learning model could be smarter than we were. And that's certainly where I was. And so the first thing I told him was, I'd like you to predict the quantum mechanical ground state spin of a transition metal complex. And I'd like you to predict the spin state splitting, which is the energy to the next lowest state. And because I'm going to tell you to train this model on DFT data, and I don't actually trust DFT to predict spin state ordering, I'd like you to predict what we call the exchange correlation sensitivity. So I'd like to know how sensitive that prediction is to the DFT model you trained on. And then because we had this toolkit, ML4Science, that used a series of DFT-trained database bond lanes, I'd actually like you to not use any structural information in making these predictions, because I wanted him to be able to predict the metal ligand bond lane so we could feed that back into ML4Science. And those were actually the three first tasks that JP accomplished in his homework. It actually worked. So spoiler alert, it worked. And then once we had developed the machinery to do that, it was actually straightforward to go ahead and predict other properties of transition metal complexes, such as redox potentials and ionization potentials, frontier orbital energies, catalyst reaction energetics, and so on. But I put up this wish list to highlight how different our interests in machine learning learning were than many of the community that has focused much more on atomization energies. Our focus was really to take this engine we had for high throughput DFT and make it faster and make it work better and allow it to explore larger chemical spaces. And so hopefully by the end of my talk, I will show you how we've managed to achieve those goals. But before we get there, just a reminder that we focus in this group on octahedral transition metal complexes. This is mostly to sandbox the task of discovery and keep things simple. I'm happy to elaborate on that offline if anyone has any questions. And we started with a series of common inorganic chemistry ligands, as well as metals in +2 and +3 oxidation states in at least 2 different spin states. And the way we addressed the exchange correlation sensitivity was actually inspired by some earlier work in the early 2010s by Stefano Savito's group as well as Marcus Ryer's work. And we specifically looked at the variation of Hartree-Fock exchange as the most essential knob to tune properties of open shell transition metal complexes. And so, as I already mentioned, there's a big trade-off in machine learning, and I think to a certain extent, it's the most exciting part, right? So there's really 3 things to think about when building a machine learning model. There's how much data we have, how much model complexity do we want to tolerate? Do we want to be able to interpret and work with that model, or do we just want the model to predict amazing numbers that we don't really understand where they came from? And then how much time can we afford to spend on generating a representation, as well as what do we want that representation to encode? Where specifically we think about representation and feature engineering in terms of how do we tell our machine learning model about the chemical problem we'd like to predict. And so, as I've already alluded, discovery in transition metal chemistry puts us at different points on this trade-off map. I think every chemical problem, as you approach it, as long as the data set size varies, chances are also your choices on model complexity or representation are also going to vary. And so I think the key thing to remember is that there's not one size fits all. But the main things to note are when we first got into this, the de facto way to think about building a representation was to hand all of the atoms and their identities and their separation in space to a model. But what we already knew from transition metal chemistry, for instance, is that what really matters the most for predicting all of the properties we care about was the metal center as well as the coordinating atoms. And so you can imagine that the right answer would be some blend between these 2 limits. So something that emphasizes what's going on at the metal center, but throws away a lot of the information further away. And that's really where we ended up focusing a lot of our effort, was trying to identify what is the best way to build these representations. As I already pointed out, our data set sizes that I'll talk about are smaller than most organic chemistry data set sizes, and they're also more varied. And this comes because it is a lot more energy, it's a lot more time and a lot more effort to generate even one transition metal complex data point for our data set sizes. And so as a result, this effort on the representation is worthwhile because we have a lot less data to work with, and we need the model to perform better on much smaller data set sizes. And hopefully I'll tell you about applications in both interpretability, but also how we accelerate discovery and take into account uncertainty. So these were our top priorities. So can we learn something from the model? Can we accelerate discovery? And can we know when the model is wrong? And I will tell you about little vignettes related to each of those. So when we did this 2 ways. I'm going to tell you about the way we first did it in JP's homework assignment in his first year of grad school, as well as the more systematic way. And the reason I still tell people about both of these approaches is that both of them actually worked. So the first way we did it was literally he and I sat down in a room and I told him everything I thought I had learned in about a decade or more of transition metal chemistry and things that we had learned here and there through different papers. For instance, things like Obviously, the metal center identity is going to matter. The coordinating atom identities matter. Things like the rigidity of the ligand, which we assess through local bond order measures, matters, as well as this one is kind of neat, is differences in electronegativity of the atoms surrounding the metal. And this one's kind of neat because when you see ad hoc engineered feature sets like this one, even in the solid state, differences in electronegativity frequently come up as a feature. So this was one that we landed on as really important. And actually where we got this from was from some earlier work we had done in looking at DFT, exchange correlation functional sensitivity, and spin splitting complexes. And so then we dug into we were a little bit short for ideas when it came to effects further out, but we dug into the therapeutic drug discovery community literature and found the Keir truncated shape index, which was a local measure of connectivity that we could apply really close to the metal. And then there are other things that you could think about, including, but when we finished with this, we retroactively called it MCDL25. It was a sparse descriptor set, really containing only information about what was close to the metal. But you can also think about properties that really depend much more on the number of atoms in the molecule. So for instance, the atomization energy, we had thrown away all of that information basically in our ad hoc feature set. And on top of that, there's also a big gap between how many atoms do you have in a system, so how a global descriptor like that, and our very middle local feature set. So we also went back to the therapeutic drug discovery community, and we looked at an approach that had been popular throughout the past 30 years called autocorrelation functions. These are discrete products of heuristic properties on the molecular graph. And they have an adjustable depth. So they're the product of properties 1 bond away, 0 bonds away, 2 bonds away, and so on. And these heuristic properties, we would just look them up in a table, and they correspond to properties of the individual atoms. What we did to revise them, to tailor them for inorganic chemistry, was we also introduced differences, as well as centering this expansion on the ligand coordinating atom or on the metal. And specifically, the heuristic properties we primarily focused on were the nuclear charge, the electronegativity, the covalent radius, topology, which is the number of atoms connected to that element, and the identity, which is just 1. And so this turns out to be analogous and be able to reproduce MCDL25, but in a much more systematic way. So for example, the number of atoms is just the 0 depth identity. In a rack definition, but also the MCDL25 descriptors are, for instance, the 0 depth ligand-centered or metal-centered Z encodes the metal and coordinating atom identities. This electronegativity difference is the 1 depth ligand-centered difference chi-rack, and so on. And I'll come back to these descriptors and what we can learn from decomposing our predictions in terms of which of these matter the most. But when I do, I will encode, I will say that we're going to call the nuclear charge and electronegativity more electronic in nature, whereas the covalent radius, the topology, which is the coordinating, the number of coordinating atoms, and the identity, I will call them geometric in nature. And then the other thing we can learn is that some of these expansions, when the depth is 0 or 1, they correspond to only encoding information close to the metal. But some of these expansions, by definition, in fact, many of them will encode information from all of the atoms in the molecule. And when we are encoding all of the atoms far away, we will call that distal. And so these are definitions I will return to. And a principal component analysis on the left here is a whole molecule representation, can reveal why we would want to do all this feature engineering in the first place. So what I've done is I've taken our data set, which is relatively modest in size, and I've done a PCA and a whole molecule representation. You can see what this is doing is it's doing a really good job of clustering the molecules by size. It puts this molecule that has 151 atoms really far away from the one that has 37 atoms. But it turns out the spin splitting energy of these two molecules is almost identical at around 40 kilocalories per mole, because the first 3 atoms closest to the metal center are almost identical of these two complexes. And so if we had infinite amounts of data, a machine learning model could easily learn the relationship between these 2 points. But because we only have a modest data set size, we're making it really hard on any machine learning model, regardless of architecture, to learn that these 2 molecules are related. Instead, if you take a look at what our local representation does, is it puts these 2 points much closer together in chemical space. And as a result, a machine learning model has a lot less work to do. And so as a result, even the MCDL25 ad hoc representation with a neural net predicted DFT spin states correctly. I won't go into the details of this except to say we first tried to use credible intervals to understand the uncertainty of the model with Monte Carlo dropout. I will come back to that in a few minutes. And that what we treated as ground truth here was DFT. So our goal here was to reproduce DFT data. For those of you who do not do a lot of transition ML complex calculations, keep in mind that we were able to achieve a root mean squared error of around 3 kilocals per mole. This is in comparison on the same data set size with a whole molecule representation of error that was about 10 times higher. And the important thing to note is that what we're basically saying is if our error tolerance is 3 kilocals per mole, that we're willing to take not the DFT result, but the DFT plus or minus a couple kilocals, we can get that answer now that we've trained a machine learning model in a second or less, instead of in the hours and likely days that it would have taken us to get those 2 geometry optimizations and get that calculation to converge. So this is where we sat at the very beginning of this. But I mentioned our systematic rack representation, and what I'm showing here is the full racks, rack 155, as well as feature selected subsets, either selected for the specific properties such as spin splitting that I'm showing here, or a universal feature selected subset that works well across multiple properties. And I'm showing the mean unsigned error. And what you can see is that MCDL25 was my chemical intuition after about a decade of being a scientist. We get about 2.5 kilocal per mole mean absolute error with respect to DFT. But racks and their feature selected subsets, which are systematically generated, actually outperform me quite a bit. So we got here to within about a kilocal per mole average mean absolute error with respect to DFT training data. And I will come back to the feature selected subsets, but we typically apply either recursive feature addition or things like random forest to rank features. And so the same thing we can again see, we could predict redox and ionization potentials pretty well. So redox here refers to the solvent and thermocorrected gas phase adiabatic ionization potential. And even though redox involves more steps, we actually do equally well as predicting IP. So the learning task is no harder, and we can see the benefit of using racks is still apparent. And then here's sort of an interesting point. So what I mentioned early on is that it's really hard for a force field to predict metal ligand bond lengths, and that we wanted the neural net to be able to replace that force field. So here's the universal force field. And what you can see is that it predicts a very wide range of bond distance errors for metal organics. Whereas with our neural net now, we can predict metal ligand bond lengths to an average error of 0.01 angstroms. So that allows us to take the organic force field that works really well, where it works well, or a universal force field, and just really only use the neural net to set that bond length very close to the end result of a geometry optimization. And so a question that's probably coming to your mind at this point is, well, what's the difference between MCDL25 and these rack subsets? Since they both work, how can we look at why one works better than the other? And so what I've done here is I've separated out MCDL25 into metal proximal versus middle versus distal features. And you can see that, as I mentioned, most of the features are proximal in nature. Middle refers to this intermediate that involves 2 atoms away from the metal. And rack 155, by definition, in the expansion, is very focused towards metal distal features. And when we apply this feature selection approach, we get down to a feature set size that's relatively comparable to how many features we had in MCDL25. And you can see the two are in agreement largely that proximal features are the most important, distal features are relatively unimportant. Where the two differ and why the rack feature subsets are outperforming is that they do a better job of encoding the intermediate middle effects of the transition metal complex. This is what I mentioned earlier when we were doing the feature engineering in an ad hoc way. We lacked creativity. So that's why this systematic approach can outperform us and also still recover many of the rules that in practice it took me a decade to learn as a scientist. Taking this a step further, we can look at how the feature selection and feature importance varies for different properties to build a lens for what's most essential in a transition metal complex. And so here I'm going to bring back that coloring that I mentioned of electronic Z or chi versus geometric S, T, and I. And I'm going to make an atom in the porphyrin now big if it's really important to the prediction versus small if it doesn't show up a lot in the feature selected subsets. And so we can come up with a feature selected subset for spin splitting depending on our random forest cutoff of either 41 or 26 features. The 26 feature one is the one I was calling URAC 26. And in both cases, we can discover that this statistical approach has learned that ligand field theory works. So the electronic properties of the metal center and its coordinating atoms are really important, whereas we can in fact throw away most of the information of the atoms from further away. They're far less important. And this is what we had seen early on with our perception that in general, the metal and its coordinating atoms are most essential. But where it gets interesting is where we compare this to other properties. So for instance, predicting the metal ligand bond length, which force fields struggle to predict, is a combination of what's going on directly at the metal and the coordinating atom, but also involves steric effects. So it's much more green, which means it's a much more balanced electronic and geometric contribution. And then where things get really interesting is if we look at a property like redox, it lights up a totally different part of the molecule. So the distal atoms become far more important, and much more of the controlling factors in redox potential are geometric in nature. And so what this suggests is that you could design the spin of a molecule independently from how you design its redox potential. And so not only have we built models that accelerate our ability to screen molecules, but we've also come up with a different way of thinking about building design rules in this space. And so you can, in fact, and we did in a 2019 paper, test this hypothesis and identify cases where, in fact, making the molecule bigger can change its redox potential without changing its spin and so on. So I will show this a couple more times, and you might find these pie charts a little more quantitative, just to say when you see more gray on the pie chart, that means it's more global in nature. When you see more blue, that means it's more local, and then red, green, and orange are intermediate. So once you've done this once, you can do this for basically any property. And so we did this for catalysis, and we get the same result for predicting something like the formation energy of a high valent metal oxo intermediate. And when we do this, we compare the properties that are essential for predicting spin and the properties that are essential for predicting this high valent oxo intermediate. And we see that the pie charts actually look fairly similar. So what this tells us is that knowing the spin of a catalyst probably tells us how likely it is to form a metal oxo intermediate. But there are some differences. It's a little bit more non-local in nature to predict the metal oxo. But we can ask, what did we actually gain in doing this? We could have maybe taken a standard approach, which is find a descriptor. This is widely done in the chemical engineering community. Find a descriptor that helps predict what the catalyst will do. And one that had been proposed that's very natural is that this high valent metal oxo is formed by going from an iron 2 to an iron 4 oxo frequently. So why not say the HOMO level from which these electrons have to be removed should relate to the oxo formation energy. And so if we do this, then we'll get a straight line. If this idea of a descriptor works, we should see that the oxo formation energy becomes more favorable as this HOMO moves up in energy. And this has in fact been proposed in this paper by Rachel Getman and Randall Snur. But in fact, this is what we see if we see our data. So this is our raw DFT data, nothing machine learning predicted. We see that you can get wide variations in oxo formation energy with almost no relationship to this HOMO level. But what we can do is we can in fact go back and train a model to predict this HOMO level. And we can do that pretty much just as well as we could train other models. And when we do the feature analysis, we see now that it should be no surprise to us at all that this descriptor fails. So not only do the machine learning models help us avoid requiring descriptors, but also helps us understand why they would fail. And that's because the HOMO level is far more dependent on the non-local structure, just like it's related to IP or redox. And it's dependent much more on the ligand structure than the metal local oxo formation energy. And so in doing this, we can routinely do specific things. Now that we have a model that can predict oxo formation energies, we can, in fact, validate our expectation that spin is an important determinant for the oxo formation energy. We can rapidly evaluate 10,000 hypothetical catalysts and see that depending on if we're in the red, blue, or green spin state, we see significant differences on spin and oxidation state for some of the metals, iron 4 in particular, governing what the oxo formation energy is. These variations are on the order of 20 to 30 kilocalories per mole, which is quite significant. Another example, this one is on ChemArchive as of last week, is that we can naturally also extend this to separations in periodic materials. I won't go into too much detail here, except to say the typical approach in the MOF community is to use only geometric information. What we did was we extended racks to periodic materials in MOFs by developing domains that maintain the chemistry associated with the MOF. So we built racks centered around the metal, racks for the functional groups on the metal, as well as racks for the linkers in the MOF. And to that, we added the typical pore geometry descriptors a lot of people use. In doing this, we improved our machine learning models, which is great, but I don't think performance on its own is particularly interesting. So what was more interesting was to see that if we went from low pressure regimes to higher pressure regimes, we could see that the chemistry of the MOF, so how much was encoded by the racks, which is in red, green, and purple on these pie charts, it goes away when we go to the high pressure regime. If we're just shoving molecules in, then the chemistry stops mattering, but it stops mattering at a different rate for molecules that are less spherical. So CO2 has more electronics going on than CH4, methane, which behaves like a rock. And so by encoding these racks, we can see where chemistry matters most in understanding MOF separations characteristics. So I'd like to switch over to for this last third of my talk, to some more technical details. And to this point, I think I've basically made the case that that we can replace DFT calculations that take days with a calculation from a neural net that would take a second. And once we've trained this, we're going to go out and we're going to find the next porphyrin. And some of you might at home might be thinking right now that I've just oversold things quite a bit and I've swept things under the rug. And this is the point where I say, yes, there are still outstanding challenges in everything we're doing. So for instance, there's uncertainty from the method that we train on. There's, which means that when we think about this in the context of high throughput discovery, if the neural net is learning, for instance, a correlated wave function theory, configuration interaction surface of data versus a generalized gradient approximation surface of data, whole regions which we think are promising materials or molecules could in fact simply be an artifact of the method. And one way we've tried to address this, I will show you two different ways, but one way we've tried to address this has been to think about training machine learning models on a family of functionals and looking at how those regions appear and disappear and which regions move around the most versus the least as we change the functional. So machine learning can actually help us understand the extent to which the predictions we make for exciting regions of material space depend on the functional. But then also calculations don't always succeed in challenging spaces like transition biochemistry. So calculations a lot of time can actually fail. And one way that we've addressed this is we've actually, and I won't talk about this further, but I encourage you to check out this paper. It's really cool from JCTC, from Chenru Duan and my group in 2019. What we actually did was develop two models to predict if a calculation would fail. In one case, we just used the chemical composition and we trained machine learning models just like to predict any other property. We trained it instead to predict will the calculation succeed or fail, which we defined as will it be spin contaminated and will the molecule fall apart, which are the two biggest failure modes in open shell transition chemistry. We also developed a convolutional neural network that took the inputs of calculations as they were running and could predict if a calculation was failing in progress. And so the very machinery we use to predict properties can also be used to introduce autonomous features to the computational chemistry workflow. But what I will talk a little bit more about is the fact that there's uncertainty in all of the machine learning models that we develop. And there are a lot of ways people have thought about addressing uncertainty in machine learning models. For instance, Monte Carlo dropout is one that I've already mentioned. Probably the most popular is to train an ensemble of models trained on different fractions of the data and look at where they disagree. But what my group has focused on is a more intuitive metric known as in our more recent work is the latent space distance, but also early on we worked with the feature space distance. And so first, how's another way we can think about addressing the question of the fact that DFT is really uncertain for predicting properties of first row transition metals. And so what I'm showing at the top here is the adiabatic high spin, low spin splitting, and the green dots are what you get from a functional with 20% exchange, and the outer regions are what you get if you just vary that amount of exchange from 10% to 30%. Lots of functionals will vary and sample as low as 0% up to 50%. And you can see that a lot of that green region sits on either side of our zero line. And so that means depending on which functional I use, I will predict a different ground state for these molecules. But at the bottom here, what I'm showing is our DFT bond lengths. So for the same range of functionals, you almost can't see the shaded region. As I vary from 10 to 30% around the 20% data, the bond lengths stay almost the same. And the high spin bond length is almost always longer than the low spin bond length. So what I've overlaid here is experimental crystal structures. And based on the bond length, you can see very unequivocally that two of these experimental complexes are high spin and two are low spin. And we can see this without any uncertainty. And so what we wanted to do was address this challenge of not knowing the right answer from DFT a slightly different way and take a look at cases where we knew the experimental bond length and see if we could assign spin states. And one place you can do this is in spin crossover complexes where multiple bond lengths have been captured experimentally. So we did this a couple of different ways in this recent paper. But what you're seeing here is you have in the dashes the high and low temperature bond lengths. And then you have what a neural net would predict should be the high spin and low spin bond length. And sometimes those points end up right on the same. They overlap, so the ANN does a really good job of predicting the exact bond length. Sometimes they don't, but in all cases, we can evaluate, is the high spin ANN bond length closer to this XRD bond length, or is it closer to the low spin? And in doing so, we can classify, if I'm looking at a structure, do I think it's in a high spin state or a low spin state? And so when we do this, we actually end up with about 96% of these spin crossover complexes I just showed you get correctly assigned in their correct ground state, and about 4% get misassigned because the neural net prediction sits between the high spin and low spin bond length. And so this is trained on just cheap DFT data, but presents another way to get around some of the challenges with functional sensitivity. And actually, when we did this in the paper, we showed that we could correct some assignments our own group had made in terms of DFT energetics, and this bond length approach is another way to think about observables that are much more robust from our computational chemistry calculations and how machine learning can harness them. So the other question of uncertainty that I think is a much more general one beyond just transition metal chemistry, but we've demonstrated it on some inorganic chemistry and organic chemistry data sets, is how do we know when our model is wrong? And so we intentionally went out for this paper and generated a data set of molecules that our trained neural net should be really wrong on, which I've shown by the data falling outside the convex hull. So the points fall outside the convex hull of the boxes where we had data before, as well as just being really far and really dissimilar from prior data. unsurprisingly, when we train a neural net on the data we have, we get a very high mean absolute error of around 8.5 kilocals per mole. So I told you we could do 2 to 3 kilocals per mole or 1 kilocal per mole, but that's only in the case where we're dealing with molecules that are reasonably similar to our training data. So these were, by definition, they contained elements we'd never seen before. They contained chemistry we'd never seen before. But you can see we do really well on a fraction of the data. So there's a fraction of the data we'd like to have made that prediction on. And then there's a fraction of the data where we have a long tail and we know we'd like to stay away from making that prediction. And so we need quantified uncertainty that tells us how do we stay away from these high error points, or how do we go out and recalculate those high error points and tell the neural net about them. And so what we developed was the latent space distance, which is the distance in the last layer of the neural network. And this enabled us to drive down errors. So if we say, if the latent space distance is too high, I'm not going to make this prediction. And in doing so, we were able to monotonically drive down the errors on the points we are making predictions on. Those are the points in green. And you can see we're making fewer and fewer predictions as we move to the left on this graph, but our error is also decreasing. So we get our error back to values that are closer and closer to our original train MAE of around 1 kilocal. But even at predicting around half the data, we can make the average error on the half of the data points we predicted only about 4 kilocals per mole. So we can define an uncertainty budget and only make predictions that are trustworthy. And the alternate, so that's called model exploitation. The alternate thing that we could do is do model exploration with active learning. And it turns out that I will show a more concrete example of this, but in a toy example of active learning, the latent space distance actually outperforms things that are more established, like the ensemble approach or Monte Carlo dropout, because it does a better job of picking out the highest error points. So now that we have a way of either sticking to the points we know or going out and learning more about the points we realize the neural net doesn't know, we can finally achieve the goal that I mentioned at the start of my talk, which is thinking about how we exploit machine learning for finding new molecules, for accelerating this challenge of finding the next porphyrin. And so we need 3 ingredients for this. We use a discrete optimization approach. So we need to define a chemical space we're going to explore that I'll call the candidate pool. We need a way to know in that candidate pool, where is the neural network certain or uncertain? So we need UQ, which I just introduced to you. And then we need an approach to optimize in the space. So ideally, for instance, in this picture I'm showing, what we'd like to do is we'd like to find the best region in this candidate pool that the neural network is confident in. And so for optimization algorithm, we did this 2 ways. One way is to think about using a genetic algorithm. There's nothing special to machine learning about a genetic algorithm. We just encode each transition malcomplex as a series of genes. We need a way to evaluate the fitness. What is special here is that we're using the neural network to evaluate fitness, so we can do that in a fraction of a second instead of in hours or days. And then the fittest survive along with some crossover and mutation. Until finally we end up with some best results. So we combine this with the uncertainty quantification approaches that I just mentioned, which in summary, we either use the feature space distance or that distance in the latent space, where the difference here is feature space is what we feed to the neural network, latent space distance is what we evaluate before the final multiple linear regression to predict the output in the neural network. And so we've actually used both of those in highly feature engineered feature sets like MCDL25. The feature space distance performs quite well, but when we have something like a RAC155 model, the latent space, which is how the model sees points with respect to each other, makes a lot more sense. And so we can combine this now with our fitness function that we normally have of the neural network matching a target we have, like say an optimal catalyst energy or a frontier orbital energy. And then we apply a penalty in this case. So this is model exploitation. We apply a penalty if we think the neural net is getting too far from the data. So, long story short, this is basically the exact copy of the picture that I showed you in the start of the talk, where we were doing high-throughput DFT screening, and we went out and we applied the same approaches now with the neural net accelerated model exploitation, and we could take what I told you took us. We were able to accomplish maybe hundreds of catalysts or materials. We now routinely accomplish scaling this up to thousands and thousands of materials, and by balancing how much uncertainty we were allowed to we were willing to tolerate, we were able to control errors on the materials we went out and discovered. For instance, on 10 molecules where we were targeting a band gap of around 4 eV, when we validated those results, we got a result that was around 3.97 eV. So we were able to control the error and go to new materials we hadn't seen before, but we're still keeping the errors not much above what the neural net training error was. But I'd like to finish now with telling you where I really think this machine learning approach to accelerating discovery can go. That's not just toy problems. It's not just showing off what we can do, that we can do DFT calculations faster, but really tackling challenges that there is no other way to solve them except with this combined machine learning approach. And so we picked something I thought was easy. I've since been told that it wasn't that easy, which was designing a redox couple for redox flow batteries. The challenges for designing a redox couple for redox flow batteries is that we want to maximize the concentration in the cell as well as the redox potential. Typical examples of these are transition metal complexes, and we also want to make sure these are stable complexes and that they are resistant to crossing over from the anode to the cathode. And so we addressed the stability and resistance to crossover challenge by designing a totally new for us candidate pool. So just to give an example, we had around 38 heterocycles that were systematically fused together to form 779 possible ligands, added around 900 functional groups, combined that with 4 metals. And the result is we ended up with a space now in the millions. So we ended up with about 3 million candidate bulky transition metal complexes. And these looked almost nothing like anything my group had ever studied before. Typically, the smallest one of these had around 80 to 90 atoms. The biggest had a couple hundred atoms, and we needed that to be stable and resistant to crossover. So we didn't have past machine learning models that were predictive in this space. We then combined our approach for UQ and optimization, and we developed 2D, what's called expected improvement, which is an efficient global optimization criterion to explore the challenge of simultaneously optimizing solubility and redox potential. And so what we did was I will show you this in cartoon, and then I will show you this in practice for my last slide. We start with a smattering of DFT data. We have almost no knowledge of the space, but we can train a neural net with, again, these are a couple hundred atoms, so just to get a handful of points is going to take some time. We train a neural net, and then we ask the neural net, what do you think of these 3 million complexes? And it'll have some ideas, and we really want to know where we can go past what we call the Pareto front. So where are we going to improve on the redox and solubility of the known compounds? And so this is where the neural net thinks these compounds are most promising. And then we take into account uncertainty in the 2D expected improvement approach. We come up with candidates. Maybe the neural net is right, maybe it's wrong. We reevaluate those points with DFT, and then we retrain the model. And so this is what this looks like in practice. So we spent a couple of weeks in the first time that we did this, and this is what we end up with. We ended up with about 100 points. So we spent 2 weeks with 64 GPUs running full throttle, and because these complexes are so big, this is all we have to show for ourselves out of 3 million compounds. But in about 3 minutes, we can find out what the neural net thinks of the space. And you can see this is lit up by the expected improvement score. Here on top of the neural net is the Pareto front in question. And so the neural net is most optimistic about specific regions with knowledge of uncertainty where it thinks it can push past this discrete Pareto front. And so we feed the points selected on this Pareto front to go past. We feed some of them over to DFT. We spend another week with DFT. So we've now spent 3 weeks with DFT. And you can see, in fact, some of those points move past the Pareto front. So some move past our first generation Pareto front, but not so much because the model was not very accurate. We do this again, and the Pareto front moves. And this time, the neural net's getting smarter. So we've now spent about 6 minutes with the neural net and 4 weeks with DFT. And you can see as this progresses on the left-hand side, more and more of our region's getting black. The neural net is getting more and more pessimistic that we can see anything better than we've already seen in this 3 million compound space. And then finally, we stop after we've spent about 15 minutes with the neural net and about 6 weeks with DFT, because we see that we're really saturating our Pareto front and not doing much to move past it. And so this is what it looks like. You can see only in the last generations do any of the points appear in the Pareto front, and also design rules emerge. So most of these complexes that sit on the Pareto front all have the same manganese high spin center with oxygen coordinating atoms and sulfur in the ring. If we want to make a sacrifice on the redox potential, which is what is shown on the x-axis, we can get better solubility if we go to really bulky ligands, but that's actually perfectly in line with what I mentioned at the start, that redox potential is very heavily tuned by size, but it turns out one great way to improve solubility is by adding just bulkier groups. And so that's part of why there's this challenge and this trade-off in how we're optimizing these materials. But you can ask, well, could we have done this another way? Could we have just randomly searched this space? And what really is the acceleration we're getting out of this combined machine learning expected improvement approach? And we can compare this to random search, and we conservatively, because these distributions are not normal, see that we get at least 500-fold acceleration. And what this means is, at least for me, when I first saw 500-fold, I thought, oh, that's not that good. But what you realize is we spent 6 weeks doing high throughput, highly parallelized GPU accelerated DFT. And what this amounts to is we accomplished something in 6 weeks that would have taken us 5 decades. So this is the difference of having an answer to a material science problem and to a challenge that we'd like to solve in a month instead of possibly not ever achieving it in our lifetimes. And so I've shown it to you in one particular context of redox flow battery design, but where my group sees it is addressing outstanding challenges in catalyst activity and stability, and many other deep challenges where multiple objectives have to be satisfied at once, mandating these large spaces that only machine learning can achieve. So just to conclude, where we started was in high throughput tools for open shell transition metal chemistry. This naturally led us down the path to building machine learning models for transition metal chemistry. I would say performance is not the be all end all of building machine learning models. It's really important to learn how to use these tools to reveal design rules and ultimately accelerate the discovery of new materials and design rules. Everything I've described is available in our code, including all the machine learning models I described and the featurizations. I just like to acknowledge the students who did the work and the funding sources. The machine learning work was pioneered in my group by John Paul Janae, but has been continued by Chen Rujwan, Deecha Nandi, Naveen, and Daniel Harper, and so on. And also, MulSimplify was first built by my first PhD student, Timmy Anitas, who graduated a few years ago. And thanks to everyone for tuning in today.
Okay, thanks a million. I guess this is a little bit usually the awkward moment because nobody claps. But I'm usually people then claps virtually on the chat box. So thanks a million for the talk. So I guess we open the floor for question. And so actually, there's already one question that came during the talk. So I just start to read that out. So this is from Rajashi Tiwari from my own group, and essentially the question is, can you explain how the distance in the hidden space really works? So how does this notion of latest space distance work?
Sure. If in the latent space, we can evaluate how similar a complex is to the prior training data. And in practice, we average over 10 nearest neighbors. So we find the 10 nearest points in the latent space of prior training data to the new point. And if that point is very far, then we say it's too far to make a prediction. And so that's an adjustable parameter. In this paper, what we did was we converted that to energy units to get like an energy error bar too. But if it's then very close, then the neural net has good support for making that prediction. So the only difference here is, I think in the drug discovery community, people had been using more the feature space distance. So how far is something in the feature space? But the latent space distance is more natural for a machine learning model, because you can think of the neural net as essentially rearranging points through the series of layers to make it more like putting points more proximal for where they need to be in order to make a prediction. So the only adjustable parameters here, again, are how many nearest neighbors you evaluate. So this can be generalized to other architectures than what I've shown, other chemical problems. We've tested it on, say, image classification tasks. It works there. The only computational cost associated with it is going to be evaluating those distances if you have a very large data set. And so as a result, it's less work than training 10 ensembles. And the main reason it outperforms ensembles here on the slide is because sometimes the ensembles can be overconfident or struggle to distinguish the highest error points from the moderate error points. So this is just intuitively, if a point is far in latent space, then it should also be one that the model knows very little about, if the model is well trained.
I might have a very quick follow-up question on that. Is there any particular reason not to use the feature space, or it's just probably, I guess if you work in latent space, it doesn't really matter what is the feature space, or you're more general. I just wonder whether it's just a matter of generality or actually perform better to work in latent space.
So we, when I showed the GA stuff with the materials discovery, some of that was in feature space with MCDL25. Mm-hmm. But when we moved to RAC 155, if you haven't done any feature engineering, and we even found this a little bit with feature space selection, is that this nice tail we were getting down at the bottom where it really has monotonic decrease in the error. We found we could get the error down most of the way, but we couldn't get all the way back to training error with the feature space distances. And this was especially true if we were working with, say, something that wasn't feature engineered like RAC 155, because there the neural network is really throwing away the aspects of the RACs that are uninformative. I think you meet in the middle. If you start with a heavily engineered feature set, then you don't need the latent space distance. And one advantage of the feature space distance is it remains more intuitive. You can identify which components of your original features, these are distinct. And one thing we wanted to do, we were never able really to make work, is understand for two compounds that are distant in feature space. Maybe it shouldn't be isotropic, maybe specific types of feature space to be different in certain variables matters more than others. But that's something we were never really able to figure out how to assess. We tried a couple things. But yeah, essentially distance and feature space is how KRR models get informed. So when you have a good feature set that has a good KRR model, then I would expect that that's just as good as the latent space. But this is a little more general, like you said.
Yeah. Okay. Thanks a lot. So actually, there is a bunch of questions actually now. There are a bunch of questions now. So the first question is from Max Garcia, who is a faculty in Trinity in the School of Chemistry, and is asking, could you please elaborate more on how you predict if a calculation will be successful or not, and how far from completion of a calculation are you able to make that prediction?
Yeah, so that is one of my, I had to pick and choose my babies, and that was one of my favorite babies, and I obviously cut it out of the, you're all learning that I try to put too much in a talk. So we had two models. One, we just try to know based on composition. So just if someone says iron hexacarbonyl, quintet, iron 2, then we'll make that prediction. And so we have to have available training data. Those models are not very transferable. So we have to go out and have some access to failed calculations. That's kind of the weakness of that approach. And so when those models transfer reasonably well, but they can't transfer to a totally new space, if you pick a totally new molecule, they need to know the relationship between composition and failure. And I think I'm actually showing the accuracy here. We were able to achieve about 90% accuracy on those models because we wanted to make the prediction just based on composition with no calculation at all. And what we're and I say no calculation at all because in practice, my group is actually pretty cool. We have a database of every calculation we've ever run. So if we've tried that calculation and it failed, we have that information. So in our case, we were already sitting on, though we generated a fresh data set for this paper, if you're sitting on a few thousand successful and failed calculations, you can train a model to make predictions without carrying out new calculations, will it succeed or fail? But that model leveled out at around 90% accuracy. And so what we found was that both the more transferable model and the model that could achieve better accuracy was one in which we fed in properties of electronic descriptors, things like the metal organic bond order, as well as the metal charge. We actually used just properties coming from the wave function and the geometry, the gradient, and that could achieve 99% accuracy. And models got more accurate the more time steps from the optimization you fed it. And our conclusion from that work was that some of this is path dependent, right? So if you change the parameters on the optimization, some of these will succeed and some of these will fail depending on what was your step size and so on. And so we'd like to turn this around in a loop that if you predict, okay, this calculation is going to fail and it's running, how do you maybe do control theory to improve it so that it doesn't actually fail? That's something that we haven't progressed very far on. But the short answer is one model, as long as you had trained the model, it could just predict new compounds, will they succeed or fail, but with less transferability than the model that used electronic descriptors. And that one could then, you could change the oxidation state, you could go to a new material space, and that picture of calculation failure was more transferable, but required, in practice, we used up to the first 12 hours of a calculation to decide whether or not to abort.
Okay, now I have two questions from Wilhelmina Kontkanen from Finland. So the first question, I guess, is about the choice of machine learning models. So the question is, how do you bias your choice? Either using random forest or neural network and so on. So how actually you select the practical machine learning model to implement? And the second question is about the diversity, I guess, of the data set. So you have a spin polarized calculation of ions that can end up in different spin state. Are those all included, and essentially how diverse is this data set?
Yeah. So the first question. So in the very first work, we would look at a wide range, all the way from lasso and random forest to neural networks. In practice, I'd say our typical workflow now is we use random forest to rank our feature addition, so to assess feature importance, but the prediction models we use are typically a kernel ridge regression model and a neural network model. And our rationale is that for our data set sizes and feature sets, the KR models, if we can get them predictive, that's a sign that the feature set either is incomplete or that the data is dirty. So we use that as a quick assessment of how well we're doing. And then sometimes when we want to be able to extrapolate somewhat, we use the neural network. In the example I showed at the end with 2DEI, 2DEI is typically used with Gaussian processes, which is closely related to KR. We actually showed in that work that a neural network was better at generalizing. And that's something we typically find in our applications. So we typically, once we've gone through the steps of making sure our data set is learnable, typically with simpler models that are easier to interpret, at that point, we then move to the neural net if we want to do some more exploratory science. I know that runs counter to what some people think about what a neural network is good for, but that's what we observe in practice versus the null prediction, let's say, from a KR model. I think if you have small data sets or especially noisy experimental experimental data sets, chances are random forest or lasso are going to outperform a lot of what these other things are going to do. So again, that's why the hypersurface depends on your aims. And then the other question is about diversity. So the tricky things we do is we always do metal oxidation state 2 or higher. And the reason we do that is because in the first row that eliminates s electrons being what determines the spin state. So we're always talking about D to D transitions. We typically look at the accessible spin states from something like the NIST database. And so what this means is for the mid row, we have low spin and high spin, which differ by 4 electrons on pairing in oxidation states 2 and 3. If we have a catalyst objective, we go to oxidation states 4 and 5 as well. And then I would say in more recent data sets, we do, especially for catalysis, we study low spin, intermediate spin, and high spin. So if we're not studying all of the spin states, the one that we're typically neglecting is intermediate spin. Or if you go to something early like chromium-3 or cobalt-2, which are early or late, like chromium-3, which is D3, cobalt-2, which is D7, those we only study low spin and intermediate spin, because to try to make, it's basically impossible to make a high spin out of that. So I'd say we're studying close to the to what can be accessed is pretty diverse. And we have unpublished work that I haven't added in where we're looking now at going to the second row, so going to 4D metals, and what is the range of transferability between 3D and 4D metals, and what are some of the challenges there. But this is for the first row, I'd say we're pretty diverse.
Okay, thanks a million. There was another question, but actually you answered already while you answered the last one, the one before the last one. So I don't see any further questions. So I'd like to maybe stop here the streaming, and I would like to thank you again for being with us today, and to all of you out there for listening. Okay, thanks a lot.
Yeah, thanks for the invitation, and thanks for everyone